Good morning, good afternoon, and good to all of our attendees joining us today for this latest Data Science Central webinar. This is Bill Voorhees, your host. I'm the editorial director with Data Science Central and also chief data scientist for Data Magnum. I'd like to start off our event today by thanking Databricks for sponsoring today's event. Databricks is a longtime supporter of the Data Science Central community, and we're honored to have them sponsoring our event today. Now, today's webinar is entitled Deep Learning and Introduction to Neural Networks, and that'll be presented by Databricks. But before we begin, I'd like to briefly review the format of today's webinar. Today's event will be an hour long. We have one presenter, who I'll introduce in just a minute. There'll be 10 to 15 minutes of Q&A following the presentation, and today's event is being recorded and will be available on datasciencecentral.com later this afternoon following today's live event. Now, I'd also like to encourage our attendees to provide questions throughout the presentation, as we'll be reviewing and presenting them on your behalf during the Q&A portion of today's event. Well, I'm very pleased to introduce today's speaker, Denny Lee with Databricks. Now, Denny is a technical product manager at Databricks. He's a hands-on distributed system and data science engineer with extensive experience developing internet-scale infrastructure, data platforms, and predictive analytics systems for both on-prem and cloud environments. He holds a Master's of Biomedical Informatics from Oregon Health Sciences University and has architected and implemented powerful data solutions for enterprise healthcare customers. So Denny, hey, thank you for being with us today. We're looking forward to your presentation. Now, deep learning has shown tremendous success, but what makes it so special? What are neural networks and how do they work? What are the differences between popular deep learning frameworks like Keras or TensorFlow, and where should you start? So in today's Data Science Central webinar, we'll show the relationship between neural networks and simpler machine learning models and provide an understanding of what gives neural networks their expressive power. We'll bring these concepts to life with a demonstration how Databricks simplifies deep learning by letting you quickly access ready-to-use ML environments, as well as prepare data and train models faster. So after this session, we'll arm you with the tools you need to run the samples yourself. Attendees will have access to the presentations and the associated Databricks notebooks. So Denny, with that, I'm going to turn it over to you. You can begin just as soon as you're ready to go.
Well, thank you very much, Bill, and thank you very much again for inviting us to speak. As Bill noted, we are talking today about the introduction to neural networks. Sorry, give me 1 second as I go ahead and try to reconnect to our slide deck. Sorry about that. Perfect. Oh, sorry about that. Okay, well, with the momentary pause, I'd like to just do a quick introduction of who is Databricks. Databricks, we are the company that accelerates innovation by unifying data science, engineering, and business. Our product is the Unified Analytics Platform powered by Apache Spark. We are founded by the original creators of Apache Spark and continue to contribute heavily to the open source code, 10 times more than any other company, and we've trained hundreds of thousands of Spark users on the Databricks platform. So in terms of today's session, note this is actually part of a 3-part series. Today's session is Introduction to Neural Networks. We also have Training Neural Networks and Applying Neural Networks. These other sessions, in fact, are linked directly within the slides themselves. So when you get a chance to download the slides, you'll be able to link directly to them. The Training Neural Networks was a session that was previously done by Bill and myself as well. So hopefully, with these 3 sessions together, you'll have a good, strong fundamental background of neural networks and deep learning. And so for today's session, just as Bill noted, but I'm just going to do a quick rehash. What is deep learning? We're going to be talking about what can deep learning do for you. What are artificial neural networks? Let's start with the perceptron, and then understanding effective activation functions. In further sessions, we'll actually be discussing things like the neural network architecture and other facets like learning rate that'll impact your neural network. But today, specifically, we're going to focus on activation functions. Okay? And as noted, these are the two related sessions, training your neural networks and playing neural networks. These are the other two sessions that will provide you some additional background. During today's session, we'll also be showing a little bit about convolutional neural networks, specifically in this type of architecture that you're currently seeing on the slide. We will go through this within the context of code near the tail end of the session, but I wanted to put it up here just to provide context of this is more or less the architecture that we'll be working with. Okay? And it's based off of the deep learning examples that are within Keras and TensorFlow, which we'll talk about shortly as well. Okay, let's talk about, first of all, deep learning, machine learning, AI, the terminology behind all this. And so the quick context is there's actually a very good NVIDIA graphic that sort of explains the context of what is artificial intelligence, what's machine learning, and what's deep learning. And so the quick context here is basically artificial intelligence. This is one of the definitions. Artificial intelligence is human intelligence exhibited by machines. And there's two actually very good examples of this where the world's best Dota 2 players, this is a pretty cool multiplayer game, are taken down by an AI, okay? And so this is some of the cool stuff that AI can do, okay? So when we go further downwards, then we can talk about machine learning. Machine learning itself, from a high level, is basically the field of study that gives computers the ability to learn without being explicitly programmed. And so a good graphics actually is sort of here on the bottom, which is if you look at purpose-built code where you've written code specifically to do a particular task, what typically happens is that you have an input and you have a program. You merge together to your purpose-built code to get an output. The output being that is the purpose of that code, right? It's to give you an output. Well, in the case of machine learning model, it's actually the input and the output that you're putting together. The machine learning model learns based on the input and the output that you receive and build a program so that way it can start predicting based on new inputs. And so that's the context, or from a high level at least, when we're talking about machine learning. And in the case of deep learning, it's specifically this context of using deep neural networks to implement machine learning. So today's session will then be focusing specifically on neural networks, which is which is the sort of the fundamental or the focus in order for us to do all of these things. Okay? And in terms of what AI can do for you, the next few slides, these all have links, and so I encourage you after this session to download the slides, and these will link to other cool demos and applications for you to go ahead and take a look at. For example, with the application of neural networks, things like object recognition or gameplay or speech or classification or language translation, things of that nature. And then specifically in the arena of healthcare, the classification or detection of potential issues in MRIs or CAT scans, or segmentation. There's a lot of cool power based on the premise that we can start pattern matching and getting machines to do that pattern matching for us. Okay. There's also some pretty amazing things, like for example, you can fake videos. One link here to the left side is an AI-generated fake video of Barack Obama, okay? And so the other one is basically turning a horse video into a zebra video in real time using GANs, okay? So again, really cool things to be looking at. So again, when you download the videos, and by the way, to provide some context, the slides and videos will be, we'll send you a link after the session that contains a link to both the slides and the video, so you can go ahead and download for your own use, okay? And then, of course, self-driving cars. Super popular context right now with everybody talking about Teslas these days. Again, AI, and or even just a cool example of turning the day into night. So we're not going to play the videos now just because it's going to take up a little bit of time, But again, some very useful or neat examples of AI. Okay, so now that we've talked about how we can use AI, let's go down the track a little bit and talk about what are artificial neural networks. Okay, and conceptually, if we talk about what a neural network is first, let's talk about a neuron. And the neuron, from a biological sense, receives a signal, processes it, and propagates that signal, or maybe it doesn't. The brain's comprised of around 100 billion neurons. And so there's a lot of network connections that are going ahead from each neuron to each other, okay? That makes up the brain. And artificial neural network they're simplistic imitations of brains comprised of dense net or of simple structures. And so we want to overemphasize the simple part. In fact, I went ahead and actually have a couple quotes from Andrew Ng shortly after this. But let me talk a little bit more here. The conceptual mathematical model basically is this. We receive input from n sources, okay? If you look at the graph here on the right, the neuron, artificial neuron or node, is basically receiving a bunch of sources, okay? The computed weighted sum is basically what's calculated here. So that's where H1 is basically your inputs, X1, and your weights, W1, plus X2, W2, and so forth and so forth. That passes through an activation function and then sends the signal to n succeeding neurons. Okay, so in other words, you have inputs, the node processes it through an activation function, and then sends it out to m set of outputs. All right. Saying that, it's a single neurons are in the brain is actually a very complex machine. And actually, the quote that I want to call out was here at the bottom. It's the note that in artificial, to really say that artificial neural networks are really nothing like what a biological brain does. Okay, we try to mimic it. It's a simplistic representation of it, but we wouldn't necessarily say that it actually does what a biological brain does. Okay, so let's call a spade a spade. Like things like, for example, even activation functions. The activation functions we use are relatively simplistic in terms of what the brain does itself. So while we can say we're trying to mimic it, we can't really say it actually does it. Okay, so that's the important call out here. Okay, and so when you look at an artificial neural network, basically it's organized as a set of layers as a black box model. Typically, there's 3 or more. You've got your input, you've got your hidden layer or hidden layers, excuse me, and then your output. Okay. For image detectors, the first layers are organized similar to as what your visual cortex would look like, but just as I noted previously, the activation functions are simpler for artificial neural networks versus biological neural networks. And so there's a quick important call out, for example, is there anything in the dimension space, like 3D? And in fact, actually, what we describe in the 3rd session goes deeper into this, but the call out is that when you're working with convolutional neural networks, it's a neural network that specifically assumes images, assumes a 3D space. And so that way we can actually process the images faster, quicker, better than versus if we were to just simply do a fully connected neural network. Okay, and so these are some of the concepts that are coming into play when it comes to the artificial neural networks. Okay, so let's go backwards and make it a little bit simplistic. So how perceptive view? It's actually just a play on words in terms of the perceptron and the immense powers of simple structures. Okay, and so let's start with that perceptron. It's a simplified binary artificial neuron. And so I'm going to ask a really simple question. Do I snowboard this weekend? All right, and so X1, the input, is the weather good? X2 is the powder good? And X3 is, am I in the mood to drive? Because in this case, I'm Seattle-based, and I want to go to Whistler. Am I in the mood to drive up the Sea to Sky Highway to Whistler? Okay, and so when I look at it that way, but then let's take an account of, like, really we need to provide all the weights, because some things are more important than others, right? If I'm an avid skier or avid snowboarder, the powder is more important. If I'm really there to enjoy myself at the villas at Whistler Village North, then the driving actually probably a little more important. So basically, this goes back to sort of what I noted in a couple slides ago. you've got your input x1, your weight w1, and it's summation of that. And if it's less than a particular threshold, your output's 0. If it's greater than a particular threshold, then it's 1. Okay, so let's piece it together now. All right, let's start again back with the no weights. All right, so it's good weather, there's a lot of powder, and I don't really care about driving. Okay, so in this case, basically, okay, it's relatively straightforward because there's no weights involved. I'm going to arbitrarily declare a threshold of 1. I'm going to say, because of the summary without any weights, it's 2, so the output is 1, because basically that's it. That's it. Just a summation of those. Actually, by the way, this says WJ. I should have said XJ, so my apologies for that. But basically, it's just the summation of those inputs. All right. All right. Now, let's add the weights, but let's talk about for the person who's the après skier, the person who isn't a shredder, isn't a boarder, isn't a skier, but they're there for the after parties. Okay. And so adding the weights in, now we're saying the good weather, that's important, but the weight's 3 out of 10. I'm just doing this as an arbitrary here, okay? A lot of powder, they actually don't really care if this powder or not, because they're really for skiing, for the parties. And they do care a little bit about driving, so it's a 5. And so what happens is you have a threshold, okay, of 5, 3 plus 1 plus 0 equals 4, and that means output of 0, because the weather's horrible, in terms of the drive up. So, yeah, you know what? Based on this premise, I am not really all that interested in going ahead and skiing because I'm the after party person. At the same time, if I'm going ahead and saying, no, I'm the shredder, all I care is about good snowboarding, good skiing, okay? In this case, the weight is good weather as 2, because I don't really care if the weather's good or not. I mean, it's great, but that's not the most important thing. For me, the most important thing is there a lot of powder or not? So yes, so that's a 6 in terms of weight. Driving sucks. I don't really care if the driving is horrible, just as long as I can get up there. That's the most important thing. So again, arbitrarily, we're using a threshold of 5. So again, a summation of WJ, XJ, well, that's basically 8. So in this case, now I'm leaning toward, yeah, I'm snowboarding this weekend, okay? So it's a simplistic concept here, but the whole point is basically that you have it's only a simplified binary artificial neuron that this Perceptron is, and yet it allows us to actually make some decisions based on various inputs and various weights, okay? All right, and one other important concept is that the Perceptron also needs to take into account of bias. So instead of just being W times X, it's actually W times plus B, B being the bias. And so, for example, a shredder has a strong bias to go to Whistler, while the après skier, not so much, okay? So that's the quick call out, all right? So now that we've talked about within the context of a binary or simplified Perceptron, excuse me, let's talk about the more common artificial neuron, which is actually the sigmoid one. And so the sigmoid one is really similar to the Perceptron, except now it's the sigmoid function W times X plus B. Okay, so in other words, we've included the bias, but now we're applying a sigmoid function around that. Okay, and so that's actually the definition of our output. And so now let's take a look at the shredder again, just for the sake of argument here. All right, again, a lot of good weather, but in this case, same X values, but our inputs, we're going to go ahead and actually do it between a value of 0 and 1. So instead of a value of 1 to 10, we're going to do a value of 0 to 1. Okay. And so, but otherwise, not everything else pretty much plays exactly the same. We have the weights, good weather 0.3, in terms of weight, a lot of power 0.6, driving sucks 0.1. Okay. And so then basically what is the calculation for the sigmoid function? You've got your inputs, which are in blue on the second line that you're seeing here, or with the highlighted in green, which is the weights, okay? So basically, that's sigmoid of 0.9, so value of 0.7109. So when you're doing a logistic regression type function, right, leaning towards 0 versus 1, I'm leaning toward 0.71. The value, return value is 0.7109. So I'm basically leaning toward the idea that I'm going to go snowboard this weekend. Okay, so fun times. All right. Cool. All right. Now that we've went through that concept, let's go one step up again, now to a simplified 2-layer artificial neural network. Okay, so you have your inputs, your hidden layer, and your outputs. Same idea as we had before, but now we're actually building more than just a neuron. We're actually trying to build an actual network, okay? And so in this case, how I've sort of defined it is that do I snowboard this weekend? There's a persona or part of me that is the après skier. In other words, I like to go and join the parties afterwards. But there's also a part of me that's very much the shredder, okay, that definitely loves snowboarding a lot, okay? And then we have scenarios like, okay, well, in the hidden layer, I'll be taking account of things like the weather, powder, and drive. So again, I'm taking that same scenario, but instead of applying it at the neuron level, I'm going to apply it actually more at the network level, which is basically how we really should be looking at artificial neural networks in the first place. Okay, so the formulations are there, but basically starts off with our input. Okay, we have your input for the two inputs on the left side. One that's the input of are you more the shredder? Or are you more the après skier? Okay, and so the for one set of persona, I'm purposely not telling you which one's which, by the way. The weights are 0.8, 0.2, 0.7, so that's highlighted here in gray, and then highlighted in green 0.6, 0.9, 0.1. Then basically that's the weights for the other particular input. Okay, and so now at the hidden layer we can calculate in sort of the highlighted in yellow 0.8, 0.75, and 0.69. Okay, now that we've established that, okay, now we'll take the formula. Let's go ahead and apply the weights from the hidden layer to the output. So again, highlighted in red, 0.2, 0.8, 0.5. So again, same calculations we did with the sigmoid neuron, except now we're applying it at the network level, not just at the neuron level, okay? And so it's a sigmoid of 1.105 based on that calculation, which means we're leaning toward 0.75. Okay, so basically the question is, as we start, like, you know, if you think about good old-fashioned hypothesis functions, hypothesis thinking, excuse me, am I going to go skiing this weekend? The output is 0.75. 0.75 basically means, I'm probably going to go skiing this weekend or snowboarding this weekend, okay? All right, so that sort of gives you a highlight of how this simplistic neuron with an activation function, which we're going to go into in a second, but with basically inputs and weights, allows us to basically make how the machine now can make decisions for you, okay? And so some really good resources actually I've linked here, okay? And definitely the good one, which I use throughout this all three sessions, which I highly recommend, is Andre Comparthy's CS231 and Neural Networks course. And this course actually, in addition to having immensely great slides, also has excellent notes and also has a full Stanford CS231 and course that's actually on YouTube, so you can follow to your heart's content. An important call out, and by the way, if you're not aware, Andre Comparthy is currently the chief AI architect for Tesla, and he was graduated out of Stanford under Fei-Fei Li. So we're talking some pretty powerful brains here that I was able to attribute heavily to. Okay. All right. So now that we've sort of established that context of the neural network, and we will go back to it in a second, by the way, okay? I want to talk a little bit about optimization, okay? And this was supposed to be a bad transformer reference, but it didn't turn out very well, so I'm just going to skip that for now, okay? So let's talk about cost function. Yeah, I know this is a linear regression example, but we do sort of need to go back in time to remind ourselves what does a lot of our machine learning models do. So let's start with the cost function, right? So, and we're going to start with a relatively simplistic linear regression example, right, which is to determine P, or the slope of the line, right? So you've got a bunch of input X and Y, right, and you're basically trying to figure out, basically we're trying to figure out how to calculate Y equals X times.
Denny, hi, this is Bill. We seem to have lost your audio. Would you check your audio connection, please?
Apologies for that. It looks like there was a slight hiccup in the connection, so I apologize for that. Hopefully everybody's back online, and so I'll go ahead and continue on the cost function perspective here. And so in the case of the cost function, like we said before, basically we're just trying to calculate t minus y, the absolute value squared, okay? And so based off of that, what we're really seeing is basically the distance between the actual value from the line, and we're trying to minimize that value. So the angle or the slope of the line, we're trying to minimize. The lower that number is, those dotted lines, the better we have, okay? And so to visualize this cost function, basically, let's go ahead and do the derivative of it, okay? So here's the cost function, okay? And then basically, on the left side is that derivative calculation, and on the right side is the actual line, okay, that we have. So as you go down that cost function curve, we're getting closer and closer to the actual, like, best value. And so in other words, this is the concept of gradient descent. Basically, we're trying to find that lowest point of that cost function, or the minima. And we do it step by step, right? Iteratively, step by step, we go down the cost function to find that minima, okay? And so a very good visualization, actually, you can see right here in this animated GIF. Basically, as you're going down the cost function and the derivative at that p-parameter, we're getting closer and closer to the best model, the best linear regression model that we can find, i.e. the slope of p, for this particular example, okay? All right. So the reason we had to bring that up is because getting the minima is actually super important for us to determine how to minimize the error and get the best model to represent this stuff, and so to represent our data. And so neural networks are no different, right? You have a context of back propagation. And what's back propagation? Well, the things that the output in the example that we use for our do I go skiing or snowboarding this weekend, was a value of 0.75. But we based on your standard training and testing, for example, we could probably figure out that, oh, wait, actually the real value was 0.85, okay? And so what's going on here is that based on our calculations, based on the gradients, what we do is we can send as part of our neural, the original value is 0.75, the model calculate, the actual value is 0.85. We basically go ahead and send the error back through the network, so that way we can try to make the model better. Okay, and so it's also known as basically this back propagation of errors, right, where the error is calculated and distributed back through the network of layers. Okay, so it's a really powerful way for us to go ahead, for us to be able to make our neural network model that much stronger. All right, so now let's talk about the neurons themselves. So, or as I should have probably called it out, it's not so much neurons activate, but nodes activate, because neurons is typically in reference to the biological neural network, while nodes is the same reference, but when it comes to the artificial neural networks. Okay, and so what is this activation function? Okay, that we're trying to work with. Okay. So basically, originally, that bias that I had referred to, remember that bias that when it shows the B, that was first proposed. Okay, so basically, it's basically a step function. Okay, well, in essence, like basically, you either are 0 or you're 1, or that's it. But that's all you have. That's what was first proposed. All right, and so what happened is that we introduced sigmoid and tanh activation functions to introduce some non-linearity to it. So that way, the threshold's a little bit, it takes a little bit more for that threshold to get passed, or a little less, depending on your scenario, okay? But the context is that it wasn't just a simplistic step function. We're just simply saying, oh, okay, our activation function is basically the sigmoid or tanh function, okay? This is a really heavily researched, by the way, sort of research in terms of what type of activation functions. So right now, for example, one of the more popular ones is ReLU, rectifier linear unit. because it's simple to compute and very robust to noisy inputs. But saying that, by the way, there's a lot of other things like leaky ReLU, Nesterov, other activation functions that come into play. I'm just talking about three simplistic ones right now, but there's actually a whole bunch of other good ones too here. Okay, so this is them. This to be candid, this particular slide may not actually age very well. Okay, because there could be by the time in a 6 months or a year from now, there will be other activation functions that will become more popular. Okay. But the reason we chose these ones because these are the common ones that are used, and especially in our MNIST scenario example that we've got here, this is the one. This is the three typical examples that are used. These activation functions. Okay, and so let's start with sigmoid here. Basically it's a nonlinearity that squashes real numbers between 0 and 1. Right? Historically, it's a very nice interpretation of a neuron firing rate. Basically, it either not fires at all or fully saturated firing. It's currently not really used as much, though we reference it and we call it sigmoid neuron. I mean, the fact is that we don't use it that much any longer because any really large values that are too close to 0 or 1 basically results in gradients that are too close to 0. Like, remember, if the value is either at 0 or 1, the gradient itself becomes 0, and it actually stops back propagation. So you can't really learn much, right? So when you have, if the values are too high, the errors can't go backwards in time, and so you can't adjust the model, and the model can't improve itself. Okay, so that's the reason why we don't use sigmoid function nearly as much as we used to. All right. So a way to solve that problem was to actually use the was to use the tanh function. There we go. Okay, sorry. And then basically it squashes the numbers between -1 and 1. Okay, so basically it has the same problem as sigmoid, that the activation saturate, thus killing the gradients, but it minimizes this zigzagging down X during the gradient descent. Okay, and so if you're going to be using a sigmoid nonlinearity, this is the preferred one, using tanh. And so if we were to basically, this is what we mean by zigzagging, right? In other words, if the output's not zero-centered, and if when you're doing that gradient descent, if the values are way too high, basically what happens, it'll zigzag around, and it'll just jump around the actual cost function curve, and it'll actually miss the minimum altogether. And that's pretty bad, because then you actually can't get to a point where you have the least amount of error. Okay, and so that's why there's the concern of the sigmoid function. Okay, and so now let's talk about rectifier linear unit. It basically has a threshold of 0. It's quite popular over the last few years. Part of the reason why is because it really does speed up stochastic gradient descent. Okay, it's also easier to implement due to simpler mathematical functions. And it's also, but the big concern, by the way, is that it is sensitive to high learning rates during training, resulting in dead neurons, okay, i.e. neurons that will not activate across the entire data set. So in some cases, we've seen scenarios where basically 40% of the network is, in essence, dead because of that high learning rate. Then basically it won't activate. Okay, so 40% of your nodes are not actually being used at all. Okay, so each activation function has its pros and its cons, but that's more or less the call out here. Okay, all right. So now we're gonna sort of do a quick little demo to sort of showcase what we're talking about here. But before I go into that demo, I just want to call out what is the tech that we're currently using here. Okay. So the tech is basically on the back end, we're using what is TensorFlow? Let's start with that. Okay, so TensorFlow itself is an open source software library for numerical computation using data flow graphs. Wow, sorry about that. It's based loosely on neural networks. It's built in C++ with a Python interface. It's quickly gained high popularity. In fact, if you look at the Google Trends here, what happened basically, it was released in November, and then by December it had become the most forked mathematical-based package on GitHub ever in 1 month, basically, or 1 to 2 months, excuse me. Okay. It also supports GPU computation. So because of that, we're basically, in our examples, we're using TensorFlow. but as our backend. But what we're doing is we're actually using an abstraction layer called Keras, so that makes it a little bit easier to work with. It's a high-level neural network API, again, based on it's a Python deep learning library. It actually runs on top of TensorFlow, CNTK, or Tiano, but we're going to be focusing more on TensorFlow in our case. It makes it to be simpler and easier to make for rapid prototyping, and so that's why Keras has become quite popular these days. So saying that, let's go ahead and show the demo. Give me 1 second here, and I will do that. Perfect. Okay, so this is an example of the notebook that we will be providing you. By the way, you will be able to download and run it yourself, okay? In this case, we're actually using the Databricks Runtime for machine learning. The reason why is because this particular version of the Databricks Runtime actually includes all of your machine learning, not all, but a sizable chunk of the machine learning and deep learning libraries that you want to use, like Keras, TensorFlow, scikit-learn. These are all pre-installed and optimized right from the get-go for you to use, okay? And so we're using the Databricks interface, as you can see here, which allows us to write code in Python, in excuse me, Scala, SQL, and Markdown. And so basically, this code, as you can see here, I'm just doing simple, quick import of your Keras. I'm using the TensorFlow backend, and then you'll see here, calls out the TensorFlow backend, okay? I'm not going to run it live right now just because it takes a little bit longer to run, but I'm going to showcase what it actually does, okay? And again, like I said, you can download this notebook yourself and run it to your heart's content. If you already have a Databricks account, then you'll be able to make use of Databricks Runtime for machine learning. If you're using, for sake of argument, Databricks Community Edition, you would then just need to install TensorFlow and Keras yourself in order for this same example to work, okay? And so, all right, now let's start off with the source data, okay? The source data is, in this case, that, for example, we're using the MNIST data set, okay? The National Institutes of Science and Technology Special Database 3. Not sure why I happen to know that, but I did, and it's propped right here. And so basically, that particular data set is basically a bunch of handwritten digits by Census Bureau employees or high school students. And it's included within Keras right from the get-go. So you don't actually have to import any data. You can just make use of it right from there. This notebook is based from the TensorFlow source MNIST for ML beginners, but it's been optimized or changed specifically for our examples here today, okay? All right, so basically what you see here, the 5, 0, 4, and 1, these are examples of some of the handwritten digits that people wrote, and that's what's stored inside this database, okay? Now, I'm not going to get too much into the code here. I'm going to let you guys sort of take your time to review that yourself. But the call out basically here is that this code, all it does is really is just downloading the data set for you to use. It happens to be stored in S3 in Amazon in this case, but wherever, when you're using Keras, basically, you don't even have to physically download it yourself. It just takes care of it for you in terms of you just call it out here, okay? And what you'll see here is that you have 60,000 training samples and 10,000 test samples. So in other words, we'll use 60,000 of these digits to train our model, and then we'll use 10,000 to validate our model, okay? And so the first question I usually get asked is, what is really that image? And so the image really is actually a 28 pixel by 28 pixel 3D structure that's been flattened into an array of size 784, okay? So the X contains that handwritten digit, and Y contains the labels, okay? And then if it says has a prefix of train, it's the 60,000 training samples, and if it's underscore test, it's the 10,000 test samples. Okay. Now, if I want to then to look at this data, for example, Y trained, that means, in other words, the label for my training data set for this particular point of the array, 25,168. You'll notice that basically it indicates it's a one hot encoding representation of the digit 9, right? 0, 1, 2, 3, and then to the end 9. So we know that the 25,168 point in the array is actually the value 9. So let's go back to X with the same value, and let's see what that number 9 looks like. Well, if you're to print it out, this is actually what it looks like, okay? So basically, lots of zeros as I'm scrolling slowly and steadily through. Not terribly interesting, okay? And then every so often, a value greater than 0. So 0.23, 0.76, 1, 0.80, 0.23, okay? But basically, this is the numeric representation of the handwritten digit number 9. So how did we get here? Well, let's print this as a 28 by 28. If I was to scroll out and do it like this for a second, you might, I doubt it to be honest, but you might be able to see the number 9 based off of the non-zero values in our 28 pixel by 20, when I print out 28 by 28, okay? It's hard to see, but it actually is there. But what we did here as part of the notebook to make it a little bit easier for you to see it is that we actually went ahead and took those same numbers and we actually just propped it into Excel or numbers. And I'm going to open a full-size version of it. Basically, what you'll notice here's the value 9. Right, all the zeros are here, and here's any value that's above 0 where we basically go ahead and put a slight gradient to it. And so based off of that, now you can sort of see the number 9. And that's what it is. Basically, this is the numeric representation of that particular handwritten digit that's stored as a 784 flattened array. Okay. All right. So now that we have these numbers that represent that handwritten digit, let's go ahead and actually start working with it. And one of the things I did want to call out prior to go ahead and showing you the code base itself is that the reason, for example, we like using Keras, or a lot of people like using Keras, is that it, for example, automatically makes use of GPUs. So, for example, when I use Databricks Runtime for machine learning, or for that matter, any other Databricks runtime, I have the choice to choose whether it's a CPU or a GPU VM that I'm picking, or EC2 instance that I'm playing with. And then what Keras does, which is cool, is that if you're running the TensorFlow backend, if there is a GPU, it'll automatically run on that GPU if it detects it. So, for example, if you want to see if any is available, this is that particular code snippet here. Basically, lets you just know, are there any available GPUs? There's another way of looking at it, but either way, there is a GPU, so we're going to go make use of it now. And Keras does that for us right away. And the reason why that's important is because running some of the code samples that you're seeing below, when I run on a GPU, it takes 1.87 minutes, but when I'm using a CPU, it's 23 minutes. And so there's a really big difference in terms of performance when I'm using a GPU versus CPU, so hence the reason for calling this stuff out. All right. Now to the heart of the actual problem. What we have here is a convolutional neural network. Now, this graphic that you see here, which I put a bunch of descriptions here, actually goes ahead and is a visual representation of this Keras code. Okay, so you notice it says here in this run CNN function, the convolutional layer of 2D convolutions. I'm doing another convolution. I'm doing a max pooling or subsampling, a dropout, flatten, dense, dropout, and softmax. Okay, right, as in here. Okay, well, that is this graphical representation of your convolution, subsampling, dropout, fully connected, dropout, okay? So this is just simply a graphical representation of your convolutional neural network. Now, in the second and third sessions of the series, we actually dive deeper into what this stuff is. For example, what is a convolution? What is subsampling? And so we're going to skip it for this particular session because, again, we were focusing primarily on the fact that of the impactor of the activation function, that it actually has a sizable impact on the ability for your neural network, on the accuracy, and the loss of your neural network, okay? And so the call out basically is that, okay, let's go ahead and showcase that. But I did want to call out that, yes, we do dive into more details surrounding this, so I didn't want to forego that basically, okay? And so, all right, so this is the neural network we're playing with. And it's, like I said, it's based off of the code that you're seeing here. Okay, and so now we're going to run it. Okay, and so this is the example that I was talking about before. If I'm using a sigmoid activation function, so in other words, in the code base just previous, I can input in. I want to use a sigmoid function, a 10H function, or a ReLU. So if I have a ReLU, you'll notice that my test loss is almost almost is a little bit more than 9%, but more importantly, my accuracy is at 97%. Okay, so that's pretty good, but now I'm going to run the same code, but I'm using the TANH function, activation function, and that's it. There's no difference. Exact same model, exact same everything, exact same seed, so we don't actually have any of the issues concerning, so we can always reproduce it. When you use the TANH function, basically our loss did drop. Okay, before when I was using sigmoid, it was 9%. Now it's 4% using TANH, but even more important than that, it's a 98.74% accuracy. So in other words, we're more accurate with less loss because we're using the TANH activation function versus the sigmoid activation function. And so this a lot of this has to do with what I had called out in the previous slides, that when you're working with sigmoid, right, because you're squashing the values between 0 and 1, any larger values end up going ahead and getting stuck at 0 at the gradients. So that means the back propagation to send those error backwards through the network, it basically isn't able to happen because it just gets stuck there. And so this is an example of where, because you're using TANH and you're avoiding some of those zigzagging dynamics, because you're squashing between 0 and 1 instead you're squashing between -1 and 1, you still have the problem with gradients, but at least it's not as extreme, so you're able to have less loss and you end up having higher accuracy. Okay, and then finally the ReLU, the one that's sort of popular these days. Okay, well, basically, this is just a verbose version, so you can actually see it. I've turned, for the other ones, I turned it off, put this value as 0 instead of 1. But basically, it just went ahead. It allows you to see for each epoch, which is sort of each full pass through the neural network. Okay, and there's 12 passes. You know, how we're doing in terms of each sample, the training sample, what their loss is, what our accuracy is, and then by the time we get said and done, what we have now is an even better accuracy and even lower loss. So instead of a almost 4% loss, now with ReLU we have, it's even better. It's a 2.6% loss, and the accuracy is even higher. Instead of 98.74, now we have 99.22%. So, and again, remember, everything else stayed exactly the same. We didn't change. All we changed was the activation function. The same convolution, same architecture for your convolution, same learning rate, same everything. We used everything exactly the same. Same in terms of the default values for each activation function. Just want to call that out, or each optimizer that we're doing. And so that way, it's giving us the best it can possibly give us for those default values. And yet, by just swapping out the activation function, bam, all of a sudden we are able to give ourselves better accuracy and lower loss. Okay? And so that's an important aspect, and this is the reason why we started off our series in terms of introduction to neural networks, just on the activation function, just because as the slides previously mentioned, it is the power of the immense power of these very relatively simplistic structures that allows us to do some pretty cool stuff. Okay, so I'm going to stop sharing the slides, sharing the screen now. I'm going to go back to the slides. And so I wanted to call out basically some additional things. First, I'd like to thank a bunch of people or a bunch of resources. So for example, I wanted to call out some excellent references that are embedded directly within the slides. So when you download the slides, you can go ahead and review the stuff yourself. Again, I want to overemphasize the CS231N Convolutional Neural Networks for Visual Recognition. It's a great course. For this session, we focus particularly on Lecture 7, which was the convolutional network section, but the reality is the entire series is really good. So if you're really interested in learning more about how neural networks work, this is a great course to take, okay? And it's free, okay? Other great references include the Visualization Toolbox and backpropagation, things of that nature. So we've propped it all here, so hopefully when you download the slides, it'll be of good use to you. And also wanted to attribute, basically, to really thank some really cool people. Tomek Drebus, Brooke Winnig, Timothy Hunter, Cyril Simon. They have been instrumental in ensuring that we have some great material, and I'm very thankful for them and all their help. And with that, I did want to hand it back to Bill and thank him for hosting us at Data Science Central. Really appreciate the time.
Well, Denny, thank you so much for that excellent presentation. And we'll get started with our Q&A session. I want to thank the audience for their participation. We had a lot of questions that have come in, so we'll do our best to get through all of them in the time remaining. And during this Q&A session, I'll leave up this screen with contact information for Denny if you'd like to get a hold of him following today's event. Denny, let's start with a real fundamental question. And do I really need to understand the math behind the neural networks and the activation functions in order to be able to work with neural networks?
Bill, that's an excellent question, and I've been asked this question multiple times, and so I really like the fact that we're starting off with this one. So the TLDR, or the short version of this answer to this question, is that you actually don't need to understand the math in order to use it, to use neural networks, excuse me. But you do want to understand the math if you want to have an intuition or how to optimize it or how to make it work well. And so this is what I mean. You can always just go ahead and look at what other people have done. And that's a great starting point, by the way. This is not a knock on it. And see that they use ReLU function, or they use TANH, or they use Sigma, right? And that's a great starting point. And then you don't really have to understand the math. You can just understand the architecture. You can understand that there are these concepts called convolution versus pooling layers. But as this series progresses, and if you watch all three, you'll notice that we actually go deeper and deeper into the math, right? We discussed a lot of the math just on the concept of that perceptron. But we actually, when we go into things like learning rates, when we go into things like the architecture itself, we really dive into that math. And so, and the reason understanding the math is important is because this is a common phrase referred to in deep learning, that when you listen to some of the greats like Andrew Ng, or listen to Andre Carpathy or Feifei Li, what they'll commonly refer to or talk about is the intuition, that you develop an intuition on how some of these neural networks work. Well, understanding that intuition often has to do with the mathematics behind it. Simple things like the distribution of your data and how that impacts how your neural network is going to operate. The size of the image, and how are you supposed to do a convolutional neural network comparison. They actually all come into play based off of the math itself. So while starting off, you might not need to know it. What I can say is that as you progress deeper into working into deep learning itself, you'll recognize that the math actually becomes important. And so again, you don't necessarily need to start with it, but if you want to start really getting good at it, you're probably going to need to know at least some of it. And hopefully that answers that question.
You bet. Hey, thank you, Denny, very much. A couple of quick definitional questions before we get into more meaty stuff. And the audience is asking, you showed the 28 by 28 convolutional neural network frame, and you referred to it as a 3D structure, but the audience says, wow, that looks like 2D to me. Can you explain that?
Oh, sure, no problem. So my apologies. The reason I say it's 3D is because, just like you said, you have the length and you have the width, but when you go further into the convolutional series, what you'll recognize is also the color bandwidth. Right now, you're seeing only grayscale because so sort of black and white. But even grayscales, when you talk about RGB channels, the red, green, blue color channels, that's actually your third dimension essence in this case. But you're right. From the standpoint of what you're seeing right now, it is a 2D representation. So my apologies for not clarifying that. So good call out.
Okay. Thanks for that clarification. Now, you talked a lot about the different activation functions. That was really an interesting explanation. So it looks like ReLU always better than TANH, always better than sigmoid. Is that true? I mean, which activation is preferred, and is that true in all training circumstance?
That's a great question. So in the examples we showed here, specifically with MNIST, for example, it is true that, excuse me, ReLU is better than 10H is better than second point in this example. And I want to make that very clear, right? In the example that I'm showing you right now, that this is absolutely true. As you progress, when you are working with other images, when you're working with neural networks that have nothing to do with images but still require some form of pattern matching, the fact is, yeah, you might find a different activation function is actually, even the old school ones are better than ReLU. Now, admittedly enough, I haven't found that yet, so I'm not going to state that you can always find it. But what I am going to say is that there are other activation functions like leaky ReLU that are coming into play. And that's why I meant by this is a heavily researched area, because as noted in the beginning of the session, when it comes to artificial neural networks, these activation functions are a relatively simplistic representation of what a actual brain's neurons activation function is. So as we progress over time and understand those concepts better, we're going to develop better activation functions. Right now, ReLU is a good starting point because ReLU itself happens to, in addition to being quite good and quite robust, it actually happens to also be relatively simplistic when it comes to the mathematics behind it. And so hence the reason for its popularity. But like I said, as you progress, this might change or this might be quite different. So again, good starting point. Don't necessarily end that way, though.
Okay. Oh, thanks for that clarification. Here's a tough one, actually. When you get started designing your neural net, especially the deep neural net, how do you decide how many layers, hidden layers, and how many neurons in each layer?
Yes, that's actually a really good question. And by the way, just as a quick call out, I'm going to answer the question, by the way, but I did want to call out that in the next session, the one on training your neural networks, that we actually also dive into some of the details quite well here in terms of how you do it. But here's your general rules of thumb if you want to note for your starting point. Okay, you start with one hidden layer, and you expand accordingly from there. And then the number of input nodes is equal to the dimension of the features. And then the number of output nodes is what you're trying to classify. So let me sort of clarify that. So the output layer, for example, I think there was a question asked about softmax function. Why using the softmax function? Okay, well, basically what we're doing is we're doing a version of a logistic classification, except it's more than just two variables. So when you talk about logistic regression, okay, you're just basically doing 0 and 1. Okay, well, in the case of the MNIST data set, it's not just 0 and 1. It's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? You have 10 output classifiers. Okay, so if you look at the diagram, for example, of the convolutional neural network, the output of that neural network is 10 different outputs. Why is it 10 different outputs? It's 10 different outputs to represent each and every one of those 10 digits that we have to work with. Okay, and so going a little off course, but don't worry, I'll come back. Why softmax? Well, if you look at basically a generalized version of this logistic regression, the analysis of it is actually a softmax regression. Hence the reason why we use softmax usually as our final step for MNIST in order for us to go ahead and get to classify those values. Okay, so now that we've established what the softmax, that's also why basically when you look at your input and output layers, right, your output layer needs to be 10 because you're classifying by 10. Your input is basically the number of features that you're going to extract out of the image in order for you to go ahead and in order for you to basically start running your model and to do your predictions. Okay, so this is sort of a good starting point. Okay, but then the reality is as you train your model and you test it and you validate it, you will do things like changing the activation functions. Okay, example 1. Or changing the learning rate of the optimizers, which we actually cover in the second session. Or number 3, the third session, which is applying your convolutional neural networks, where we actually change the architecture. And right back to your original question, Changing the architecture is exactly the call out on the number of layers you have and the number of potential nodes you have. And so right now, this session by itself doesn't really cover everything, but it should cover at least the beginnings of it. Follow all 3 sessions, and you should be able to cover all the context you'll need to be able to sort of grok the number of neurons to start off with and the number of layers to start off with. Hopefully that answers that question.
Oh, hey, Denny, thank you for some great answers to some very good questions. And for those of you that asked questions that weren't answered today, we'll be sending all the unanswered questions to Denny and the Databricks team so they can follow up with you after today's webinar. Now, I have just a few quick announcements. If you'd please mark your calendars for November 14th, that's tomorrow, and that's our next DSC webinar, which is Creating a Thriving Culture of Data Analytics at EY. Now, today's taping will be available for on-demand viewing later today. You can find that on the home page of Data Science Central in the Webinar tab, located at the top of the page. And I'd also like to remind you that past webinars are available on demand at datasciencecentral.com. And if you haven't had the opportunity to view them, I encourage you to take a look. They provide some very useful insight into a wide variety of topics of interest to our data science community. Well, this brings today's webinar to a close. I'd like to thank our audience for their attendance and thoughtful questions. A special thanks again to Databricks for their sponsorship, and particularly to our speaker, Denny Lee, for his insight into today's topics. So this is Bill Voorhees. I'm very pleased to have been your host for today's event. I look forward to seeing you all again on November 14th, tomorrow. Have a great day.